Thank you all for joining me this morning. I know it's the first session of the last day, which is always a little hard. So thank you all for being here. I'll see if I can keep this informative and entertaining. I'm going to try to pepper this with a bunch of takeaways throughout. So if you get nothing else out of the talk, hopefully you can leave with a few kind of actionable insights that you can take to your real-world applications of these types of problems. So I'm going to be talking to you today about tuning the untunable, which in itself is kind of a conflict of terms. But what this really means is how do you take very expensive to train deep learning systems and kind of get the most out of them? What would otherwise be potentially intractable in terms of hyperparameter tuning or architecture search? How do you start to kind of get a foothold on this problem and potentially get some good results? So I'm going to start with some background that this work builds upon, do a little bit of a literature review, and then dive into a case study. Excellent. And we'll do questions at the end, but if anything's really pressing, I can take it in the middle as well, too. So first, how did I get here today? I've been tuning big, complex simulations and models for more than a decade now, stretching back to my PhD work at Cornell, where it was mostly tuning like big physics simulations at Los Alamos and Lawrence Berkeley labs across the Bay. Went to Yelp and was tuning some of their machine learning systems in the advertising system and basically realized that this was a super prevalent problem, especially as computational techniques get more advanced, these models get more sophisticated, data gets larger and larger. It becomes more important to make sure that you're efficiently tuning these complex systems. So wrote some open source called Mo, or the Metric Optimization Engine, still available on GitHub via Yelp. It's been forked a couple of times. I think the most maintained version is from the lab at Cornell. But this really started to show that this was a very, again, prevalent problem in industry. So started a company around it about 5 years ago. That company's SIGOPT. We provide an experimentation and optimization platform, basically a layer that sits in the middle of a machine learning stack that allows you to kind of bolt it on top of a bunch of different models, allow you to get insights from different experiments that you're running, do model search and hyperparameter tuning, as well as manage resources for the actual training and tuning itself. So bolts on top of PyTorch, Keras, TensorFlow, whatever you guys are using, and then whatever cloud or infrastructure. I know everybody here is using GPUs or you wouldn't be here. But the goal is to kind of be that middle layer to do this as efficiently as possible. And I'm going to talk just for a second about how this works because it's really important for the rest of the talk. So what I'm going to be talking about in general is black box optimization for tuning these systems. And optimization here means tuning the configuration parameters that go into affecting these systems. So I'm not talking about the individual stochastic gradient descent methods, although those often have hyperparameters you can tune. I'm talking about tuning the system holistically in a black box fashion. And that means that we don't get access to the model or the data. So we're not doing auto differentiation or anything like that. What we're doing is saying we have this time-consuming and complex system that we can sample very sparsely. How do we, as efficiently as possible, go through an optimization feedback loop, suggesting configurations to try, observing their performance, and using that information to gain insights and do optimization and provide better and better results. Excellent. So as I said, this is based off of some joint work that we've been doing with NVIDIA for the last few years. It really builds upon a lot of that work. I think this is my third or fourth talk here at GTC. So in the beginning, it was all about just how do you go about tuning these systems in general, or maybe how do you look at things if they have kind of competing objectives. A lot of times, if you have a very time-consuming or expensive to sample system, you might say, I want the highest possible accuracy, but I want the smallest possible training time. That's one way to attack this problem. But it still requires you to evaluate that entire system to be able to see what that training time was, or what that end inference time was. So this can be helpful, but again, if it takes days or weeks to train your model, it could still potentially be intractable. Another thing that you can potentially do is throw better and better hardware at this. So this was a survey we did with NVIDIA and AWS showing how if you take different computational architectures and then you take different tuning techniques, the speedups you get from each of these is multiplicative. So if you get a 10x speedup by switching from a CPU to a GPU, and another 10x speedup from switching from something like a traditional kind of randomized search or grid search to a more intelligent search, it ends up being 100 times faster than doing the standard methods kind of themselves. So this is great, but again, we need more. So in some recent work that we published about a month ago with NVIDIA, we showed that if you kind of take into account the complexity of the entire parameter space that you're tuning. So this is incredibly important if you're doing like neural architecture search, or if you're trying to search over different stochastic gradient descent methods that might have overlapping parameters, you can get another speed up here. So again, all of these are kind of incremental gains of saying, okay, how do we maybe encompass timing as one of our objectives? How do we use hardware to really get a good speed up? And how do we take advantage of the search space itself to get some really some good speed ups as well? And this comes up all over the place in industry and in applications. So a lot of you are applied data scientists, machine learning engineers. You're doing this day in and day out. And you see that this comes up often. But the long training cycles can really be this massive barrier to even wanting to attempt any of these methods. These are all nice, and they can add benefit, but they add benefit making the strong assumption that you're able to tune your system at all. If it takes a week to train your model, you might not be able to do any of these things. So how do we address those types of problems? And that's really the focus of this talk today. Of course, all of these things can be put together to create some really powerful results, but we need to be able to attack the problem at a high level to begin with. So this is the main thing I'm going to be talking about, and the takeaways are going to be coming from this. So how do you efficiently tune models that take a really long time to train, just to be super explicit? And this is super important because models are getting more complex. They're taking a longer time to train. The amount of computational power required to do some of these more cutting-edge techniques and get some of these cutting-edge results is increasing pretty dramatically. You'll notice that this is on a log scale here, and it's just continuing to increase as more data becomes available, as more hardware becomes available, and of course, as the complexity of these techniques continues to grow year over year. And we're seeing a lot of really cool applications. 10 years ago, some of these things were considered kind of unsolvable or intractable. But now we have very readily available speech recognition tools. Deep reinforcement learning is getting really popular. This is a screenshot of the AI5, the Dota 5 from OpenAI, a collaborator of ours, as well as computer vision problems becoming incredibly important as self-driving cars and some of these things start to roll out into the real world. But I'm preaching to the choir here. You wouldn't be here if you didn't already know that these things are starting to happen. But the real question is, how do we, as efficiently as possible, get the most out of these systems and techniques? And, won't be a surprise, hardware can definitely help. As the computational power gets better, we can get better and better gains. As we start to use some of these really fancy machines that you can see out on the exhibitor floor, we can continue to kind of attack some of these larger and larger problems. But as I said in the beginning, this is only a piece of the puzzle. And by being more efficient with the way that we do tuning, we can get some of these multiplicative gains out of it. So there's been a lot of different approaches to this historically in the literature, from just being able to parallelize your tuning, so don't do things just completely sequentially, but be able to kind of look at many things simultaneously, to using more and more intelligent tuning methods. So instead of using maybe a more standardized approach like a grid search or a random search that doesn't take historical context into account, and is akin to trying to climb a mountain by maybe jumping out of an airplane and just hoping you land at the peak, and then just doing that over and over again. You can use techniques like Bayesian optimization or other intelligent methods. Underneath the hood at SIGOPT, it's an ensemble of many different Bayesian and global optimization techniques, kind of auto-selecting and tuning that for you. But beyond that, again, we can adapt Bayesian optimization. We can adapt some of these intelligent sampling techniques to take advantage of the fact that we may not be willing to or able to sample the entire system. And that, again, is what I'm going to be talking about today. So we're going to start with a really simple idea. We can use information from partially trained models to more efficiently inform hyperparameter optimization. So the great thing about deep learning is it's a relatively iterative process. Like, you get partial information as you're going. After the very first epoch, you're able to kind of see the learning rate and how it's the learning curve and see how it's converging potentially to a solution. You can also use subsets of data. You might be able to come up with a completely different model that you think is just a lower fidelity version of the system that you actually want to tune. So it feels like there should be some way that we can exploit this information in order to more efficiently do this. And that's exactly what we're going to do. And there's been a lot of really great work in this over the years. Some of the previous work here that's very popular in the literature is work like hyperband and early termination. The idea here is try a bunch of stuff and then kill the bad stuff early and let the good stuff keep going. So you can think of it as random search, but stop poor performance. And hyperband in particular, so that's early termination, hyperband in particular kind of does that along an intelligent grid. So at different checkpoints, kill bad performance, and then spin up new random things. But the problem is the underlying kind of tenet there is you're just doing random search a little bit more intelligently. You're doing random search where you allow things to die if they don't look good. So it does converge with random search over time because at the end of the day, that's the underlying iterator that's drawing these new suggestions. You're not intelligently deciding what to do next based off of things that you've learned. It's also making pretty strong assumptions about the convergence of these methods. So it's assuming at a high level some level of monotonicity in the fact that things will continue to decrease over time, which you see in this purple one doesn't happen, and that order is relatively preserved, that we're not going to see kind of massive shifts in something that looks bad early, looking very great late. So these strong assumptions can sometimes hold, but very often, especially as these systems get more complex or you start to tune the system in a more holistic way, looking at maybe tuning feature representations to the actual model selection and architecture search, to the hyperparameters. Maybe that's being fed into another system like an algorithmic trading strategy. All of a sudden, some of these strong assumptions maybe stop holding as true. So there's been a lot of work in kind of extending this. This was a great paper that was published at NeurIPS recently. And basically, we want to build upon this prior research and basically say, how do we apply this to Bayesian optimization? How do we apply this to the idea that we should be able to leverage information we're getting from these lower sampled tasks to more intelligently suggest the next one? Don't just go back to the well and grab another random one, but say, I have some pretty good information for how I think this is going to perform. Let's use that instead. And in practice, this works pretty well. The concept here is for different tasks, so in this case, this could be you're using 1/28 of the training time, 1/28 of the data, whatever it may be. This is a task that costs 1/28 as much as the full task cost. And we want to be able to leverage this information to guide us. And you can see that for the partial task, we get some high-level, like non-granular information. It's maybe not enough to kind of resolve the actual local optima within this specific region of interest here. But it is enough to tell us maybe don't sample the right half of this space. So again, very cheaply, we can get that information, kind of inform our priors, inform the individual like covariance kernels that go into our Gaussian processes, kind of tune our optimization system in order for it to be as efficient as possible once it starts sampling these incredibly expensive tasks. Make sense at a high level? Great. But again, similar to hyperband or early termination, we're making some pretty strong assumptions here. And that can be fraught with peril. In this paper, another NeurIPS paper, these cheap approximations can maybe give us a foothold, but we need to make sure we are aware of the bias they may incur on the overall system, or that the lower fidelity tasks, these cheap approximations, might actually lead us completely astray. So you could imagine subsampling the data, for example, ends up causing you to completely overfit. And then when you apply that same information to the full cost system, you end up getting an extremely brittle result. Or you could imagine the early learning curve has no correlation with the end result. Or in a big complex system, let's say you're building an algorithmic trading strategy or something like that, looking things at the granularity of weeks or months might not give you any information if you're actually trying to build a high-frequency trading simulator. So we need to make sure that we take into account the correlation of these low-fidelity tasks, these cheap approximations that we can sample, and the actual full-fidelity task that we actually want to sample. So let's say the green curve here is the low-fidelity task, and the blue curve here is the high-fidelity task. So we actually want to be able to optimize the blue curve. And you can see these functions are, I'll tell you they're not correlated, but they're not correlated. They don't look correlated. And when we look at the individual kind of acquisition function, or how we would rank what we sample next, you can see that the green function down here doesn't provide a lot of information. It's a lot of noise. It doesn't actually provide any sort of utility insofar as giving us information of what to sample next, and we'll end up just continuing to sample the blue function. So we've given the system the ability to sample a low-fidelity task, and it just chooses not to because it doesn't actually gain anything from it. But if these are a little bit more correlated, if we can actually get some information, so again, we're not assuming that they're identical, but we're assuming that they are similar enough that we can learn things about the general shape of the response surface or whatever it may be. Now all of a sudden we can say, okay, maybe over here they both want to sample this region. But again, if we just purely look at it in terms of information gain or expected improvement or probability of improvement, some of these classical methods for deciding what's the most intelligent thing to sample next, we're still only going to sample the high fidelity version. Because again, that gets us the most information, so why not sample it? This method has no concept of the cost. But if we normalize for that, and we let it know that, hey, I want the highest maybe expected improvement per second, or the highest information gain per unit cost, now all of a sudden, we get this interesting result where sampling the low fidelity region actually gets you more information than sampling the high one. And we can sample that and repeat, and eventually start to converge into only sampling the high-cost task because we don't get any new or relevant information from the low-cost task. But again, doing this in a really intelligent way where we're explicitly ignoring it if it's uncorrelated and leveraging it when it makes sense in terms of an information gain or whatever acquisition function we want to apply to it. Cool. So why should you do this? Does it actually work? How does it compare to these other methods? There's a great paper that goes into this, Klein et al. It's up on arXiv, where they basically took a bunch of different data sets and for a support vector machine, so a relatively simple model, compared it to a bunch of different multitask, Bayesian optimization, and early termination techniques. There's lots of other comparisons from like early termination or hyperband to things like random search or vanilla Bayesian optimization too. So you can kind of cobble together some of these results to get a clearer picture of how it works. But let's say that these are the top 5 relative to kind of the standard methods. And what this paper showed was similar to previous results, kind of a naive vanilla Bayesian optimization approach. So just take a Gaussian process with a Matern kernel and throw expected improvement on it. This is kind of the standard. If you look at one of the like thousands of open source projects that are out there these days that have kind of ballooned out, this is kind of the approach there. Hyperband does pretty well against that. But once you start to look at maybe more complex acquisition functions, start to ensemble these methods, the intelligent techniques start to get a bit of an edge. But for these time-consuming systems, being able to do multitask optimization gets you quite a bit further. And again, you'll see that these are log graphs getting to the similar test error in orders of magnitude less total wall clock time. And this is all well and good, and this kind of points us to that this might have legs. This might be tractable. But again, if I will jump back a slide here, we took relatively simple data sets, like some of our old favorites, MNIST, And we applied it to a relatively simple method, a support vector machine. Support vector machines can be very time-consuming, expensive, especially with the size of the data set and the kernels that you use. But at the end of the day, it doesn't necessarily look identical to a deep learning system. And so that's what I'm going to be talking about for the remainder of this talk, is given these same techniques, can we actually accelerate the optimization, improve the performance of some kind of common deep learning tasks with common architectures? So we're going to take kind of a fun image classification data set here. This is the Stanford car data set. 16,000 images of a bunch of different cars. This is somewhat of a pathological data set too, because it's something that I think if I picked a random person in the audience, you might not be able to score super well on it, because given a snapshot of a car, you need to be able to get its what car it is, so the actual manufacturer, the make, and the year. So being able to say, oh, well, that's a Tesla, doesn't count. You need to be able to say, that's a 2016 Tesla. So very difficult problem, but there are kind of minutia within the images that allow a sophisticated deep learning algorithm to be able to kind of pick this out. And we're going to go to an old classic and just use ResNet. Probably not even worth reviewing this. A lot of people in the room are very familiar with this. Very classic way to do image classification. The breakthrough here was creating these kind of residual units that allowed you to kind of convey information through the actual neural network. There's a lot of classic architectures that were built from this, and there's kind of canonical versions of this that we're going to be using for the tuning itself, namely ResNet 18 and ResNet 50. So we're going to do two different things here, and there's going to be an interesting kind of takeaway that wasn't super intuitive to everyone who was working on this project here as well. So one is we're going to take the much more complicated ResNet 50, which corresponds to kind of the size of the architecture, and the somewhat more simple ResNet 18. For ResNet 50, we're going to pre-train it on ImageNet, and then we're going to only tune the fully connected layer. And then for ResNet 18, we're going to fully fine-tune the entire network. So the concept here is maybe having it trained on an image classification task already should give it kind of good enough results. We'll see what actually happens. Then we're going to show how multitask optimization can get you further performance boosts by tuning the hyperparameters associated with like stochastic gradient descent and some of the other kind of tunable parameters within a ResNet model. So we're going to compare kind of the impact of tuning methods as well as kind of what happens when you tune various hyperparameters. So there's a lot of things to tune in these systems. In practice, some of our customers tune up to dozens or 100 different kind of parameters for some of their really complex systems. For this one, we're going to just pick kind of 7 classic hyperparameters. Learning rate, the learning rate scheduler, batch size, whether or not we use Nesterov, weight decay, momentum, and the scheduler step. A lot of these are based off of the original ResNet paper. Cool. The results are actually really compelling, though, because this was the somewhat non-intuitive result. There's a massive gap between doing transfer learning and tuning the fully connected layer and fully fine-tuning a much less sophisticated architecture or much less complex architecture. So you'll remember here with this data set, there's 196 different options. So accuracy doing just random classification is about at 0.5%. So this is a relatively difficult problem. We're not flipping a coin here and doing worse than flipping a coin. But at the same time, the gap between just the baselines of using the standard hyperparameters was pretty massive. Both these data sets took about the same amount of time to train, 4 hours on an Amazon P2 instance, but got very different results. So here's a good takeaway. Use a less sophisticated or less complex network, but fine-tune it. You might get much better results than kind of just naively throwing transfer learning at a problem, even if it seems at a high level to be a very similar problem. ImageNet versus this car data set, I mean, very, very similar. So the second takeaway is there's always stuff left on the table by tuning the actual hyperparameters. So again, when performance matters, you want to make sure that you don't just use the default in the same way that just using transfer learning from ImageNet doesn't necessarily get you the best result here. Using the hyperparameters from whatever paper you drew or the last project you ran or whatever intuition you have about the 7-dimensional space may not translate perfectly to this other problem. And the other thing that's really great about this is by applying this multitask optimization system, what we're able to see is at the beginning of the experiment, we're sampling a lot of small tasks. It's doing what we would expect it to do, learning as much as it can in this very cheap setting, where maybe in this case we only let it train for 1/10 of the total training time. And then towards the end of the experiment, it starts to sample more of these medium cost tasks, and then by the very end, it's sampling only the full cost tasks, which is what we really care about. At the end of the day, we don't want to give you the hyperparameters that tune the low fidelity tasks the best. We want to give you the hyperparameters that tune what you actually care about the best. And you can see that it learns and gets a pretty good accuracy at the beginning, just sampling partial cost approximations, and then eventually they converge together as it really zeroes in on that full cost task. And that distribution shifts over time. Another interesting thing about this is when we look at the individual configurations on a dimension per dimension basis, we can see that large swaths of the space were ignored because the partial cost tasks kind of shone a light on the fact that it didn't perform well. So think back to that original graph that I showed you when I was talking about multitask, how we got that really kind of grainy, low-resolution version of the response surface by sampling that task that was 1/28 the cost. It was able to point us in the right direction, but then we really needed to zoom in on it. And that's what you're seeing here with these individual tasks being sampled. We learn that the middle of this learning rate space, this kind of log transformation of the learning rate, is the place we're sampling. And then we start to sample more and more, start to layer in more expensive tasks, and then eventually get to that best result. And you'll see this, I don't show it here, but weight decay behaves similarly. The more important these parameters are as it's doing this kind of multi-dimensional joint optimization, the more likely it is that it kind of was able to find that early information and drive you towards sampling intelligently in the expensive setting. And this has become kind of classic in these papers too, kind of pointing out some specific examples, some fun things to cherry pick about the model. Again, if you look at the untuned model versus the tuned model, these are things that the untuned model got wrong, the tuned model got right. There's some interesting things around the fact that individual kind of croppings of cars didn't perform super well. The model itself cannot read, which is kind of an obvious result, but this is something where I would expect the audience to be able to say, oh, this says Lamborghini here, it's probably not a Chevy. But again, the model is able to pick up the distinctions between various years of a specific make that you might not have ever seen before, but can't do something like this. Another thing that confuses it is context, so busy images. It thought that this was a convertible because it was able to see the tops of all of these seats and this person, when in fact it was trying to classify this van here. And then multiple cars also confused it quite a bit, where it tried to kind of take the average of the two cars or like try to jam them together instead of classifying them individually. So one takeaway here is this was kind of a fun data set, and no one really cares whether or not this model was able to classify these cars perfectly. But at the end of the day, you're probably working on real-world applications that might have real influence and impact in it. A lot of our customers are like in the algorithmic trading space, like 2 Sigma and Tower Research. If their models go wrong, they can lose a lot of money. We also work with the US intelligence community. If their models go wrong, bad things happen. So think about this when you're doing your own work. What's the impact of that extra 3, 4, 5%? And it could be the difference between millions of dollars. It could be the difference between something making it into production. But at the end of the day, you want to make sure you don't leave any extra accuracy on the table if you can get away with it. And you can always cherry pick some fun examples, but just jumping back here, results are what you actually really care about. Cool. The other thing worth noting here is a lot of times when people talk about random search or hyperband or some of these things, they like to beat up on these more intelligent methods because they presume that they're purely sequential. That's not necessarily the case either, especially in this multitask setting where, again, because we're trying to get this informed information about the space in general, we're able to leverage parallelization pretty effectively. In this case, sampling 20 tasks asynchronously in parallel throughout this entire process. So even though it did 220 effective full cost tasks, it was able to do that over only 11 full cost tasks worth of time, or about 45 hours in this setting, because we were able to leverage that kind of asynchronous parallelization and intelligent scheduling. And then here's the money slide. At the end of the day, this can make a real impact on how much performance you get versus how much money and time you have to spend to get there. So this was the entire point of the talk. When you have a time-consuming and expensive to sample system or network, in this case it was only 4 hours to train, but again in practice we see things from some of our customers in the days or weeks range. Being able to do this orders of magnitude faster really adds up. GPUs are great, but they're not super cheap yet. So here again we see that by just comparing it to something like a randomized search that took 20 times as many evaluations to get to actually a worse performance, it costs quite a bit more money and then quite a bit more time. It is embarrassingly parallel, so this is something you could extend out if you had kind of unlimited access to resources. But often, again, in practice, we find that people usually have a cap on the number of machines that they can have. So even if something's embarrassingly parallel, they might only be able to run 20, 50, 100 at a time, unless, of course, you're someone like Google or OpenAI. And the real thing about this is really democratizing the ability to tune these expensive models. If you look at some of these papers or blog posts, really incredible results, but they use hundreds of thousands of hours of computational time. And again, that's great. It pushes the field forward. But when we talk to our customers day to day, they don't have access to that. They have access to a handful of GPUs. They need to get a result in a week because they have a deadline coming up or whatever it may be. So by doing intelligent multitask optimization and leveraging an intelligent optimizer underneath it, you can get to the same level of results, the same style of results, but do it in a fraction of the time. And as models get more complex, as they get more sophisticated, this becomes more and more of a pressing issue. So high-level summary and takeaways. This is a tough challenge. We have a lot of empathy for you. Hardware is a big part of the solution. This would be completely intractable without some of the amazing technology that NVIDIA has put out. But you really need to augment that with intelligent tuning solutions as well. They can further accelerate this either in iterative ways like we've talked about in the previous work, or in completely transformative ways like the multitask optimization that I showed here today. And they typically perform well, not only in the wall clock time, making this a tractable problem, but again, getting you better results, which at the end of the day, if you're working on something that matters, which I hope all of you are, you care about performance, and you really want to make sure you apply your domain expertise and get as much out of the system as possible, but you don't leave extra performance on the table by just not tuning or trying to do 10-dimensional optimization in your head or doing a handful of random selections. So there's lots of stuff that this was built upon. There's the documentation for multitask itself. I sprinkled in links to all of the different papers from the incredible researchers that have continued to push forward in this field throughout the talk. That's available online. This example itself is also fully reproducible. Shoot me an email at scott@sigapp.com if you'd like to dive into it more. I can connect you with the team that built it. But we're also hiring, startup in San Francisco. Again, more and more people are running into this problem every day, from the financial services industry to the intelligence community to people building recommendation systems and the same models that you guys build every day. And our goal is to help empower those experts and help really accelerate and amplify the impact of modelers everywhere. And so if that resonates with you, come talk to me and join our team. Thank you all.